So imagine trying to understand a movie, right?
Yeah.
But not by watching it play out second by second. Instead, you lay out every single frame on this massive table.
Oh, yeah. Like all at once.
Exactly. You stare at all of them at the exact same time, and you calculate the statistical relationships between the pixels in frame 1 and the pixels in, like, frame 10,000.
Right, which is incredibly powerful for processing information.
It is, but it is fundamentally entirely unlike how a biological brain experiences time. I mean, we are essentially forcing our models to spatialize time, and for the past few years, the entire machine learning field has basically been locked into this arms race of brute spatial scale.
Yeah, we build a transformer, we feed it 1 trillion tokens, expand the context window.
2 millions of tokens now, right?
Yeah.
And then we celebrate a fraction of a percent drop in the loss curve. But, beneath that success, there's this fundamental architectural limitation. We're scaling massively, but we are still really struggling to build universal reasoning models that genuinely generalize over time.
Well, because the transformer architecture, I mean, it's incredibly effective at pattern matching across a static context window. But its relationship with sequence, temporal reasoning, it's completely synthetic.
Right.
It requires seeing the entire context simultaneously to make a prediction. Because to compute self-attention, you're performing this dense matrix multiplication where every single token has to attend to every other token.
Which creates that brutal O of n squared computational complexity.
Exactly. So as the sequence length scales, your compute and memory requirements just explode. But a biological system, it processes information dynamically as it flows through time.
Yeah, it updates an internal state continuously. It doesn't need to maintain a discrete record of literally every sensory input it's ever had just to understand the present moment.
Right. And that brings us to what we're looking at today.
Yes, welcome to today's deep dive. We are unpacking this ArcSieve paper from September 2025 that tackles this exact discrepancy. It's titled The Dragon Hatchling, the missing link between the transformer and models of the brain, by Kosowski, Uznański, Chorowski, Stamirowska, and Bartoszkiewicz.
And they've engineered a completely new large language model architecture.
Right, they call it Dragon Hatchling, or BDH. And if you are an ML practitioner or a data scientist or a mathematician listening to this, this is really essential material. I mean, you are likely already tracking the evolution beyond standard attention mechanisms towards state space models.
Yeah, and this paper isn't just, proposing another theoretical brain model. It presents a highly performant, inherently interpretable alternative to the transformer.
And it rivals GPT-2 scaling laws, which is wild. But the authors actually root their motivation in historical context, going all the way back to the early days of computer science with John von Neumann and Alan Turing.
Right, because both Turing and von Neumann were just intensely focused on how uniform, scale-free biological networks like the human brain possess these powerful intrinsic properties for computation.
Let's define that really quickly. A scale-free network in graph theory is a network where the degree distribution follows a power law.
Yeah, so you have a few hub neurons that are massively connected orchestrators, right? While the vast majority of neurons only have a few local connections.
Which is exactly like biological ecosystems, or even human social networks, honestly.
Exactly. And Turing and von Neumann, they hypothesized that this specific topological structure is what allows biological brains to handle temporal generalization so naturally.
Through, like, local interactions and dynamic state updates, rather than global, dense computation.
Right.
But wait, so I have to push back here. If biological scale-free networks are so clearly superior for generalizing over time, why are we stuck relying on transformers right now? I mean, we've had spiking neural networks and neuromorphic computing concepts in the literature for decades. So is this just a hardware compatibility issue, or do we lack the mathematical frameworks for training locally interacting networks at scale?
It's actually a severe convergence of both. Historically, trying to map a network of locally interacting neuron particles onto modern computing infrastructure, it's just been disastrous for efficiency.
Because of the hardware design.
Right. Modern GPUs and TPUs, they're highly parallelized engines. They're optimized for dense, uniform matrix multiplications, specifically GMM operations.
Yeah, general matrix multiply.
Exactly. But biologically plausible models, they typically rely on sparse, irregular, and asynchronous updates.
So when you try to run a highly irregular graph model on a tensor core, the core just spends most of its time waiting to retrieve data from memory, right? Instead of doing actual math.
Yeah, you hit a memory bandwidth wall almost immediately.
Yeah.
And furthermore, on the theoretical side, we just lack the mathematical formulations to prove that sparse, local graph-based interactions could actually scale.
Like to match the linguistic reasoning of dense attention mechanisms.
Right. The theoretical proofs just weren't there to justify the immense cost of engineering around the hardware limitations.
Okay, so how did the specific team bypass that memory wall? Let's get into the mechanics of the BDH architecture. The authors define it mathematically as an attention-based state space sequence learning architecture.
Right, but the core primitive isn't a dense layer. It's a scale-free, biologically inspired network of nonlinear, locally interacting neuron particles.
Which is a huge shift because in a standard large language model, you have dense all-to-all attention within a given layer. Like every token looks at every other token.
Yeah, but in BDH, the fundamental operational unit is that system of interacting particles. It operates entirely as a graph model.
And the interaction network relies on a highly modular structure with that heavy-tailed degree distribution we mentioned earlier.
Exactly. It forces the network to route information through specialized, heavily connected hubs rather than, broadcasting every piece of information to every single node simultaneously.
And despite that massive structural divergence from what we normally do, the empirical performance is staggering. I mean, the authors report that BDH exhibits transformer-like scaling laws.
Yeah, they demonstrate it rivals GPT-2 performance on language and translation tasks.
Across a scaling curve from 10 million to 1 billion parameters, and using the exact same training data.
Which is huge. Matching GPT-2 parameter for parameter on identical data using a biologically inspired architecture is just a massive validation.
But I'm stuck on something here. As a data scientist, graph models, especially ones with heavy-tailed degree distributions where a few nodes hoard all the connections, they're notoriously clunky on GPUs.
Oh, absolutely.
I mean, GPUs crave dense, predictable grids to keep their arithmetic intensity high. So how on earth did they run a scale-free graph efficiently enough to rival GPT-2? Are they basically just disguising a graph operation as a dense matrix multiplication?
That is actually the pivotal mathematical breakthrough of the paper. So think of a graph model like a chaotic, tangled web of string. GPUs hate that web. They cannot process it efficiently because the memory access patterns are entirely unpredictable. What the authors did is mathematically comb that string into straight, predictable rows.
Structured matrices.
Exactly. Structured matrices that a GPU's tensor cores can process all at once without losing the original localized connections.
Wow.
Yeah, so while the underlying conceptual model remains a graph of interacting particles, they engineered a formulation of the sequence learning that maps directly onto parallel associative scans.
Okay, let's definitely define associative scans for the listeners who might be purely on the application side of ML.
Sure. So in modern state space models like Mamba or S4, researchers realized that if an operation is associative, meaning the grouping of operations doesn't change the result, like with addition or matrix multiplication, you don't have to compute a sequence step-by-step sequentially.
Right, you can compute partial results across the sequence in parallel blocks on the GPU and then just combine them.
Exactly. The BDH authors took the local, sparse interactions of their scale-free graph and formulated the temporal updates as a series of associative operations.
So that allows the local interactions to be computed in a way that maximizes arithmetic intensity.
Right. They found a mathematical isomorphism that basically satisfies both the biological plausibility of a local graph and the rigid hardware demands of a modern tensor core.
That's brilliant. So they retain the sparse, localized, temporal properties of a graph model, but project it mathematically into a space where the GPU can chew through it without hitting a memory bandwidth wall.
Exactly.
Yeah.
Which establishes BDH as a highly performant practical alternative.
Okay, but because BDH relies on these local interactions, we really have to look at how it actually processes data in real time during inference.
Yeah, the working memory.
Right, because in a transformer, working memory during inference is managed by the KV cache. You're appending dense key and value vectors to a massive, growing tensor for every new token. So how does BDH handle working memory without an infinitely expanding KV cache?
Well, the working memory in BDH relies entirely on synaptic plasticity. It utilizes Hebbian learning and spiking neurons.
Wait, really?
Yeah. Rather than storing a separate record of the past in a cache, the model alters its own structure.
Okay, so Hebbian learning, that's the classic neuroscience postulate, right?
Yeah.
Neurons that fire together, wire together.
That's the one.
To visualize this, I like to imagine carving a ski track in fresh snow. The first time you go down, it's shallow, friction is high. But with every subsequent pass over the exact same route, The track gets deeper, faster, more defined.
Right.
So the physical structure of the terrain changes based on the activity happening on top of it.
That ski track analogy is a good start, but let's actually take it a step further to truly capture what is happening in the BDH architecture.
Okay, how so?
Imagine that the snow itself is actively reaching out to pull the skis into the fastest possible route.
Oh, wow.
Yeah, the network topology dynamically reacts to the input, and the authors empirically confirm this behavior within the BDH model during training and inference.
So what did they actually see happening?
They observed that specific individual synapses actively strengthen their connection weights whenever BDH hears or reasons about a specific concept while processing language inputs.
That's insane. So the interaction network actively recruits nearby neurons to form functional modules on the fly.
Exactly.
Okay, but if you're an ML engineer listening to this, your alarm bells are probably ringing right now. Because standard practice dictates that inference is static. We train a model, we freeze the parameters, and deployment is just passing data through frozen matrices.
Right, static weights.
So the idea of a model physically rewiring its synapses and updating its weights during inference sounds like an absolute deployment nightmare.
It does sound like one, yeah.
Are the authors saying the model is physically updating its state dynamically just by listening to a prompt? Because doesn't that completely redefine what we consider inference in ML? Like, how does that work without the model destabilizing or overwriting its core knowledge?
It's a great question. And it forces us to entirely rethink the boundary
Right.
between a model's parameters and its hidden state.
Right.
Because in a transformer, that boundary is a hard wall. The parameters are the frozen weights, and the hidden state is the transient activation passing through them.
But in BDH?
In BDH, that boundary is fluid. Inference is a dynamic, continuous updating of a localized graph. The baseline weights, the foundational knowledge learned during training, they act as a stable prior.
Okay, so the base knowledge is safe.
Yes.
Huh.
But the immediate synapses governing working memory, they are modifying themselves in real time to maintain the specific temporal context of the prompt.
So the temporal context isn't stored in a massive spatial buffer like a KV cache.
No, it's stored in the newly strengthened transient synapses of the network itself. And this transient plasticity naturally decays or resets for new tasks, which prevents the model from permanently destabilizing those core weights.
Which perfectly explains the high modularity we discussed earlier. So as the model processes a prompt about, say, quantum physics, certain hubs of neurons become highly connected based on those specific concepts, right?
Exactly.
Creating a specialized transient module just for that prompt.
Yeah, and this leads to one of the most profound implications in the paper.
Which is?
The authors state that because this model utilizes spiking neurons and Hebbian plasticity so effectively to process sequence learning, it moves way beyond simple biomimicry.
Oh, I see where this is going.
They propose that the BDH architecture actually explains one mathematically viable mechanism that actual human neurons could use to achieve speech and language processing in the biological brain.
That is heavy. They're suggesting they've mathematically modeled a viable mechanism for human cognition, not just built a better text predictor.
Exactly.
And, if the model's synapses are physically strengthening around specific concepts dynamically, that naturally transitions us to what is arguably the holy grail of modern machine learning right now.
Interpretability.
Interpretability. The paper emphasizes that BDH achieves monosemanticity. And I know polysemanticity makes standard LLMs act like black boxes.
Yeah, where a single dense neuron might fire for cats and also for financial derivatives.
Right, because the model is compressing data into complex superposition. But how exactly does this new architecture force a neuron to only learn one concept?
Well, it comes down to two strict mathematical constraints placed on the activation vectors within the BDH architecture. They must be sparse, and they must be strictly positive.
Okay, why positive?
Because in a standard transformer, activations can be negative, which allows the model to use destructive interference. It can layer multiple concepts into a single dimension and then use negative values to cancel out the noise it doesn't want at any given layer.
And that is superposition.
Right. And it is entirely unreadable to humans.
So by forcing the activations to be positive, usually through mechanisms mathematically akin to a specialized real U function, BDH cannot use destructive interference.
Exactly. It's mathematically forced to assign discrete, separate concepts to individual sparse neurons.
Okay, but the authors use this specific phrase, interpretability of state. And they explicitly note that this goes beyond just looking at the interpretability of individual neurons or isolating
Right,
features.
it's a bigger picture.
So, what exactly is interpretability of state, and why is it inherently possible in a scale-free graph, but basically impossible in a transformer?
Think of it this way. With a transformer, trying to understand its reasoning process is like trying to figure out a complex recipe by tasting a fully blended smoothie.
Okay, I like that.
Even if you apply advanced post hoc techniques like sparse autoencoders to identify a specific flavor, to find the cat neuron or the finance neuron, you are still only looking at isolated activations at a frozen point in time.
Right, because the actual state of the model's reasoning is distributed abstractly across a massive, high-dimensional dense manifold and a sprawling KV cache.
Exactly. You cannot map out the causal chain of its logic. But with BDH, you are literally watching the chef pull ingredients from the pantry, chop them, and put them in the pan.
Because you can observe the physical topology of its working memory.
Yes. You have a network of locally interacting particles with sparse positive activations, combined with synapses that dynamically strengthen via Hebbian learning.
So interpretability of state means you can literally observe the physical structure of the model's thoughts at any given millisecond.
Because there is no negative superposition hiding information. You can map the heavy-tailed graph and see exactly which conceptual hubs are connected, how strongly they're firing together, and the exact sequence in which they formed.
Wow. You are reading the reasoning of the machine as a physical, localized map.
Exactly. The mechanisms that allow BDH to generalize over time, the local interactions and synaptic plasticity, are the exact same mechanisms that make its internal causal state entirely transparent.
That is incredible. So synthesizing the sheer scale of what Kosowski and the team have presented here, the Dragon Hatchling is really a fundamental paradigm shift.
It really is.
They've engineered a scale-free state-space sequence model. It leverages spiking neurons and Hebbian learning to dynamically process temporal information, all without a massive KV cache.
And it matches the scaling laws of dense architectures like GPT-2 up to 1 billion parameters.
While forcing monosemanticity and interpretability of state through sparse positive constraints. And it achieves all of this through a mathematical isomorphism that allows graph operations to run at peak efficiency on modern GPU tensor cores.
Yeah, they solve the hardware problem and the math problem at the same time.
Exactly. So for any ML practitioner or data scientist listening, this signals a critical pivot. The pursuit of universal reasoning models does not mathematically require infinitely scaling, opaque, dense attention matrices until we exhaust the global data supply. The path forward might look much more like the biological brain, shifting away from brute spatial scaling and adopting the locally interacting dynamic plasticity of scale-free networks.
The transition from spatial data processing to localized temporal dynamics, that really is the frontier right now. And, it leaves us with an unresolvable, somewhat staggering thread to consider as this research progresses.
What's that?
Well, if we now possess a mathematically rigorous, heavy-tailed graph of locally interacting particles, and this graph can dynamically rewire its own physical synapses in real time to generate complex language.
Yeah.
And the researchers mathematically demonstrate that this mirrors the temporal mechanisms of actual human speech. At what point does optimizing the interpretability of state in an artificial neural network cease to be a computer science diagnostic and begin to look exactly like mapping the mechanics of human consciousness itself?